All right, we continue. We continue now with yet another topic. We do statistics and the glaciers and so on. Others do critical thinking, chatbot, etc. The maths of climate change are difficult. And the question is, could we bring some of it into schools? First of all, it would be good to have like an idea, the global idea of what math is necessary to understand climate change. And that motivated me to invite another member of the LAMMA, we described that this morning, who is a specialist about the mathematics of climate change. And I was very grateful that Alberto Ortolani said yes to this invitation. And his mission is to tell us about the difficult math of climate change in a way that we understand at least a bit. And I am very grateful that you will now make this effort. So the word is to you, Alberto. I understand that you're a mathematician. Alberto is a mathematician. It's also...
No, I'm a physicist.
Oh, a physicist. Ooh, even more difficult. A physicist. But they need a lot of math, so we know. So physics and maths are very close together. In any case, we are grateful that you have said yes, and I am very enthusiastic about your telling us about the maths and the physics, perhaps, of climate change.
Exactly, Laura, because you asked me the very hard work to do. So probably I'm sure in my presentation it's too long with respect to the time I have, so I have to cut something. Don't worry. And let's say, we will see. Because there has been a lot of interesting input this morning and the beginning of this afternoon. So in the last part of my presentation, I will deal more with data than with mathematics about climate. So some evidences, I guess that something of this are not so spread even in the, let's say, scientific community, not working on climate, of course, in the one working on climate, yes. Honestly, I'm not a specialist in climate and just in some parts of the climate science. And so I will do my best to try to transfer you what I think is relevant for, let's say, a word that it's very important, in my opinion, which is awareness. So we need people, we need students to be aware of, let's say, the things that we really know and the other that we, let's say, know with a less precision. So from this point of view, let's start because the time is running. Let me share the screen. Where you can see that I've a little bit modified the title and add also from mathematics of predicting extreme weather changes also some physics of climate, which is the last part, but in a way that are strictly related. First of all, we are very worried all about extreme events, which are one of the things happening, let's say, we think about due to climate change. This is a general opinion, but it's something more than an opinion. And let's say, as a definition, an extreme event is, I'm just reading, a time and place in which weather, climate, or environmental conditions, such as temperature, precipitation, drought, or flooding, rank above a threshold value near the upper or lower ends of the range of historical measurements. This is a definition that you can find in the National Agency American of let's say, for the environmental, from the environment of the USA, which is NOAA. And there you can see how extremes can be, let's say, represented statistically. Now we have 3 curves here. And let's say in the top one, let's say there are tails that define extremes that can change because this curve moves. Consider, for example, that temperature increase, or that can change because the spread change. So you can have more extreme events, because in the second curve in the middle you see that it's, say, less. The peak is lower. So you have more probability also for extremes, or because the shape of this curve changes. So there are several things changing in the climate that can bring you to have a change in the, let's say, probability and so occurrence of extreme events. This is what happened a few days ago, very close, so a very few kilometers where I'm speaking now, which was close to Florence and Campi Bisenzio, another flood, 7 casualties. So let's say a very sad, let's say, situation. And it's not the first one. And let's say, we have to know, and we know that now every, let's say, autumn, we know, I'm speaking about Italy, we know that in some places a flood will happen. This is not the situation that I remember when I was a young guy. So floods were, let's say, not so common as are today. Anyway, how can we forecast them? It's very difficult. Just a slide. This is a slide, let's say, summing in a very rough way the mechanism generating precipitation. So just to predict precipitation, you have to model a process that happens at a very small scale. When I say small scale, I'm not saying about few kilometers. I'm saying something that can be even centimeters, because I mean, you have condensation that has to be, let's say, facilitated by the presence of aerosols, because in case you don't have aerosols, we cannot have precipitation. This is a very interesting, but it's another story. I have no time to speak about it here. And then there are several processing happen that, let's say, this small condensed drop can be to increase, to let's say, grow up. So in droplets, then eventually form ice crystals and then stay together in order to, let's say, not to be able to buoyant. And in this way, precipitation can happen. So just to, let's say, model a process like this, it's a very complex process that happens at a very small scale. But when we think about atmospheric processes, they are not related only on the gases present, or let's say a water vapor or whatever in the atmosphere, but they are strictly related to their boundaries, especially to the one on the Earth's surface. So I mean, the interaction of the oceans with the land and with the other, with the biosphere, so forests and so on, are absolutely relevant, essentially because let's say through these boundaries, there are the exchanges of energy, so heat. There are the exchanges of, let's say, matter, essentially water, but also aerosols made by pollens, smokes, and so on, which is very relevant for a number of processes of radiation absorption and also precipitation generation, as I mentioned before. And then there is also friction. So I mean, for the surface wind, which in turn condition what happens in the higher layers. So we cannot treat atmosphere without managing also the interaction with the other parts of our world. So essentially, weather and climate are Earth system sciences, not just fluidodynamic sciences. If we, let's say, for the moment, limit to the atmosphere, the governing primitive equations are essentially the one that you probably know because of even your high school studies. So it's the Newton law, conservation of momentum. The first law of thermodynamics, essentially the conservation of energy, the continuity of equation, so conservation of mass, and specific conservation of the water mass, because I mean, we assume that the water can change the state from liquid to gas to solid, even in the atmosphere, but not, let's say, change in other substances, let's say, apart from some negligible chemical phenomena that are, I mean, that are not so relevant from the point of view of weather or climate. And then we have the ideal gas law, which, let's say, it's the equation of state that makes in a relationship the parameters. These are parameters like, I mean, temperature, pressure, and density, essentially. These are the equations written in the most simple way. And if you see, for example, the ideal gas law, you have to be aware that, for example, it's not so correct, and that there are some correction even put in in let's say, present models, just to account for deviation from this ideal behavior. Here there are thermodynamic equations, so the one I was saying before about the first principle of thermodynamics, and this is the heat, so that is, let's say, take into account also the interaction with the main engine of all the dynamic of the atmosphere, which is the solar radiation, and also have to take care about internal processes like, let's say, the ones related to precipitation, because when you have precipitation, you have a change in the phase state, so from vapor to water, drop water, or to ice crystals, with release or absorption, if things happens in the opposite direction, of latent heat. So I mean, when you have water, let's say when you have condensation and then precipitation, where you have condensation, you have a release of latent heat. So a warming of the air parcel where it happens. And this in turn, let's say, affect the dynamics of the atmosphere. Of course, this is in an environment which is not flat, which because of the let's say, circular spherical shape of Earth, almost spherical shape of Earth, because of all the orography, and in a rotating planet, so with our apparent force that have to be put inside this equation, specifically centrifugal force and Coriolis force, which determine the basics, let's say, behavior of the general circulation. You can imagine, I mean, these equations are partial derivative equations, non-linear, so not solvable analytically. You need numerical approaches, and you need initial condition to start this equation, let's say, in a way that are, how can I say it, hooked to the real nature. So I mean, you have to start from measurements, and so this equation can then help you to, let's say, transfer the information at the initial time up to the future in order to make a forecast, or even a climatic scenario. But if you consider the other interaction I was mentioning at the beginning, you can imagine that these are a number of additional complex equations. So you have just an idea of what it can mean to make, let's say, an atmospheric forecast or a climate forecast. The longer is the horizon of the simulation you are interested in, so what is called the lead time, and the higher is the importance of this additional interaction. Because of course, if you have to make a forecast for, I don't want to say a few hours, or even one day, you can use average values, for example, for the Earth surface, the ocean's sea surface temperature, and so on. But if you want to go further with days, I mean, you have to consider also the dynamics of these other, let's call, environments, and so the interaction, and so the change in the, let's say, in the exchange of energy, mass, and so on, I was saying before. Of course, this is much more important when you think about climate scenarios. So you have to think about also, even also to things that can happen at the geological level. I was saying all this cannot be solved analytically, so we need to, let's say, divide it into grids and do it numerically using, let's say, high-performance computer platforms that are available. And it means that you have to solve this equation and to transfer the information from one grid point to the other for a number of, let's say, what are the prediction variables that are shortly listed here: temperature, humidity, pressure, moisture, and then wind, and so on, clouds formation, and so on and so forth. But considering the number of points that you have to put here, this is the global model. So I mean, something which has not to deal with, let's say, horizontal boundary condition, because it resolves all the Earth. So you have a limit on the soil with this interaction I was saying before, on the Earth surface, sorry. And another limit, which is the hand of the atmosphere, which is the hand means where the atmosphere is stable, it allows us to put, let's say, average condition, not influencing the meteorology of the first, let's say 10 kilometers or 20 kilometers of the Earth. And we are speaking about a million up to billions of parameters running. So that's what we are dealing with. All this to produce a map like this one. This is a map of forecast for exactly this moment, made 2 years ago by the European Center for Medium Range Weather Forecasting, which is ECMWF. Let's say, produce this global forecast at the resolution of, let's say, kilometers.
Alberto, excuse me, your audio is not working fine. Can change without headphones using the computer mic, please? Make a test.
How is it now?
It's better. Try it in this way. Thank you.
Okay, let's go. So what I was saying, so this is a map from the global forecast. But if you want higher resolution, in order to have higher precision, you can run a model that can solve smaller scales with respect to the one that are approximated by global model. And so you use information from global models or forecast from global model, and you take a frame from this one in which you put your higher resolution models, and you run it, let's say, hoping to add value in the sense that hoping to resolve the physics at smaller scales that, let's say, global circulation model cannot resolve. So this is one of the things, for example, that we do at LAMMA and generally in all regional meteorological centers. And we produce, so in a domain, let's say, covering Europe, for example, a forecast with respect to the one that are all over the world made by ECMWF. I don't know why. Okay. This means that we have a lot of approximation and source of errors to keep into account when, let's say, thinking about the accuracy of the resulting forecast. So first of all, we have something which is unavoidable. We have to represent a continuous medium in a discrete grid. So, I mean, we cannot resolve all the physical scale up to, let's say, microscopic scale, but we have to stop at the very macroscopic scale. Normally, let's say the scale now we can resolve even in our center, like our it's 1 kilometer or a couple of kilometers. Sometimes can be even a little bit more resolved, but atmosphere makes a lot of things also in subgrid. Think, for example, about turbulence or things like that. So you have to approximate these subgrid aspects, and then you have numerical approximation of the governing equations, because I mean you are dealing with machines that have a limited precision. The parameterization of subgrid processes was mentioned before. It's another source of approximation. So it means that at a given level of resolution, you have to stop with physics and going on with statistics. Essentially, consider, for example, a convection precipitation or the mechanism I was showing at the beginning. I mean, you have to take let's say, parameters that can bring to this kind of processes and say, okay, when I have this temperature, this humidity, this profile for the atmosphere or temperature, humidity, and let's say presence of aerosols and so on, I guess statistically that I'm going to generate this kind of precipitation at the scale which is not resolved by the physics of the model. So this is, of course, statistics is not physics, and this brings, of course, errors. You can improve it through data analysis and so on, or you can improve it going to run smaller scale models, but you need more computing time or more computing power. So let's say you need a compromise. Then there are the schemes related to coupling with the biosphere, with let's say ocean, with glaciers, poles, ices, and so on. So cryosphere and so on. So from this point of view, also this coupling has a number of approximations that brings errors. And then you have the errors for the initial condition, because I mean, you have measurements which are not available for each grid point. And so from this point of view, you have an incompleteness of initial and conditions and of boundary conditions for the same reason. And at the same time, I mean, each measurement has its own error due to the measurement process. So, I mean, all these errors, let's say, are transferred to the simulation and tend to grow. I mean, the let's say, related error in the forecast tend to grow with increasing of the forecast lead time, as Valentina showed this morning shortly during this her presentation. So the first point to say, okay, now we know approximation errors produce errors in the forecast that tend to grow with increasing forecast lead time. And how we can reduce these errors? So essentially, how we can improve these forecast skills, especially, this is a question especially relevant in case of, let's say, extreme event. And how we can improve the error impact on forecast. Improving in the sense how we can manage, estimate this error in order to be aware of the precision of the acute, let's say, precision of the forecast we are producing. First, to reduce the errors, we can add information over in the first part of the simulation. This is the process called data assimilation. Here you see, for example, a forecast, let's say, represented by the blue line, and some observation represented by these green circles, white inside. What you do is to merge observation with the model to push the model towards the observation, not to push towards, not over. Because I mean, the model have a consistency, physical consistencies that observation not necessarily have, because they are taken in different places normally. So I mean, there is a problem or a presentation that they can have. So I mean, you want to, and they have an error. So you want to preserve the consistency of the model, but you want to add the information in order to link better the model with the real, let's say, atmospheric dynamics. And up to the time you can do it, so to the present, then you do it, and then you have to go on with the forecast, hoping that this forecast is more linked to the real conditions, so let's say is capable to provide you more accurate forecast, especially when you are dealing with probable extreme events. The process statistically is let's say, represented here. This is these pictures that is taken from this paper, very interesting. And you see that you have a model in the green with an error, because I mean the model has an error intrinsic also to the approximation I was mentioning before. Then you have an observation here in blue, which is what is truth, which with an error because of the observing limitation. And the merging is to produce an analysis, this one in red, which is stays, let's say, in the middle, not exactly in the middle, but let's say in a weighted middle between the model and the observation. And from this one, you can start your forecast that, of course, at the beginning will have less errors than the starting error of the model, growing with time. So at a given time, you know that let's say, the error has increased again. But at the beginning, you can gain something. Of course, you can do it several times if you have more than an observation step. So you can do what is called the filtering, producing what is called here in each time of observation analysis, which is the best representation you can have of the real situation because of not optimal merging of model and observations. Then you can do it several times and then go on with forecast, or you can use this data to, let's say, fill the database for other application. For example, today also for training machine learning approaches to forecast, but this is another story, but just to mention how this kind of activities can help also these applications. A better way to produce a database is not making filtering but smoothing. So I mean, going also from the backward in the simulation, so from the present into the past. So merging all the available information in order to produce the best estimation of the situation. Here is not something made for forecast, but it's made for reanalysis. So I mean, for having a global optimal representation of the Earth atmospheric state for, let's say, essentially climatologically or training or other application like training, machine learning and so on applications. The role of satellites in this one has grown up. So as you see in this diagram, the most of the information presently arrives from satellites in different ways. Let's say passive sensor, active sensor, radio occultation, and so on. But there is also the, let's say, provision of information very relevant from a local sensor made by, let's say, in situ observation, weather station, surface weather station, or something which is, say, provide you information over the higher layer of the atmosphere, thanks to aircraft measurements or radio sondes, which are, let's say, balloons launched and go up in the atmosphere and provide you local measurements of a number of parameters that can be used in an assimilation process in order to make initialization or to improve also the initial part of the model in order to gain information and to improve what are the forecasts. Then, if you want to map, in any case, the errors, the best approach, I mean, about data simulation, it's a very complex thing. I want to say that there are several methods. I was a couple of weeks ago in a workshop which lasts 5 days, international workshop, just focused on data simulation, in order to let you know how this subject is complex and how much is the effort on the research side. So I mean, I've simplified a lot just to give you an idea, but the mathematics, which is, let's say, on the background of this process is very, very complex and with a variety of solutions and so on. So, but you know, just to give you an idea of what we can do to improve forecast. The other is to map errors. Map errors is important because, let's say, to know the precision. So I mean, how we can trust a forecast. Valentina this morning showed you a map similar to this one. What I want to stress is that here, for example, what we do, we know the initial condition errors. So we, let's say, change a little bit the initial parameters. I say we, but these are things made by, let's say, global centers. It's a complex work in order to, let's say, generate a simulation a little bit different one to the other, according to the errors of initial condition. And then at the end, you can have the distribution of your forecast. Consider here that, for example, with starting from a simple representation of temperature, like this could be a sort of Gaussian, so in any case, a bell-shaped distribution. At the end, it's not guaranteed that you have a bell-shaped distribution of the forecast. In this case, of course, these are 3 peaks. And so this can be something, the end can be very different from what you, let's say, from the starting point, even at the level of the shape of the distributions. This is a real case, spaghetti, let's say, graphs that that also Valentina showed this morning, but I want to stress this one. Here we have 2 days forecast. I mean, we have a forecast starting in 2 days of, let's say, of the same day of the year, but one in 1995 and the other in 1994. Same place, same model, same initial condition. Everything is same, except that there is one here from one simulation to the other. And as you can see, on the left, you have, let's say, what is comfortable simulation, in the sense that, I mean, this spaghetti picture, let's say, the ensemble, show that there is an increasing in uncertainty going, let's say, almost smooth in time. while on the right, you see that this the divergence of solutions after 2 days are really very relevant. I mean, here at the third day, you have an uncertainty much higher than the 10th day of the picture on the left. So the message is, take care that a forecast can be even, let's say, very different, the accuracy of the forecast from one day to the other, according to, let's say, the dynamics and the uncertainty of the initial condition that you have, thanks to the dynamics and to the, let's say, physical processes that are acting. And another thing to see here is that, I mean, normally we are used to relate essentially on a deterministic, let's say, model, which is just one of this line. And in this case is the control one, which is the black one. Then you have the dot blue one, which is the analysis. So what I've explained to you before. So emerging of this model with data, essentially something which is almost the truth of the atmosphere. And you can see that this truth, after some days on the left panel, after, let's say, 5 days, goes very far from the control one, so from the deterministic forecast. So it's still inside the spaghetti representation, but it is far from what you could expect if you look only to one deterministic forecast. And this is more dramatic on the right panel. So you can understand from this how it's important also to be, let's say, to have an estimation of the error of forecast, because this has consequences in the decision that you can take after this. So take-home messages. Data simulation and sample approaches allow to reduce and estimate errors in forecast. And this is a process which is very important, based on observations and on the capability to make several simulations, also on computer power. So we need, of course, increasing computer power, and this is happening, but we need also to increase accordingly the number of observation and the real-time availability. So this is the reason why we, let's say, install more and more, let's say, measuring stations, but also why we go on with satellite observation, because if we want to improve the capability of forecast, we have, first of all, to improve the capability of observing our atmosphere, and not only, also the other environments related to the atmosphere, and to put it in the model in an optimal way in order to improve our forecast. Now, question. Climate change means weather change. In another word, global warming means local weather change. I could answer in a simple way now. Yes, if you put more energy in a system, the energy will change the dynamics, this additional energy. And if we change the dynamics in a complex environment like the atmospheric one, I mean, the Earth system one, of course, we have change also in the local weather phenomena. But have a look a little bit more in details on this aspect. First of all, let's say this morning and also in the afternoon, we have spoken about global warming and the problem that people has in understanding, sometimes in believing, and so on. But have we, let's say, really elements to say that global warming is not only scientific opinion, but is an unquestionable fact? I try to answer having looked at these pictures. I'm sorry not to be there, because at this point of the presentation, I would ask you what you think are the more representative data or things related to global climate change. And probably you will say well, increase of surface temperature or something like that, or sea level or some other things. Here we have a sort of number of representation of these things, but we have to be aware that in these, let's say, graphs, you have to rely on the goodness of science and the honesty of scientists that have made the measurements and provide you these pictures. So I mean, if you don't believe in science, on scientists' honesty, you can doubt about all of these things except one. One is the mountain glaciers. Why I'm saying so? Because, I mean, if you think about surface temperature, I mean, this afternoon, Noah put a question to you, which is the increasing, how temperature has increased. And I mean, the number was 1.2 degrees at the moment, with a target of 1.5, probably not reachable, and so on. But we are speaking about 1.2 degrees, where if you go outside of your let's say room and you measure temperature in I don't know, in the road in front of the exit, I don't know where exactly you are, but where you have probably a road or things like that, you take a measurement. If you go on a grass place close 100 meters, you find another measurement. If you go close to the river, to the lake, if you have it very close to you, let's say, you find differences that are higher than this. And then you have a fluctuation, diurnal fluctuation, fluctuation due to seasonal fluctuation due to the fact that if you go on a hill, let's say, temperature can change rapidly and so on. So, I mean, of course, when you say that the global average temperature has increased of 1.2 degrees, you make a lot of, let's say, how can I say, you are confident that scientists have done it, but you cannot say it's clear that it's really happened. And if you think about sea level, we speak about few centimeters, and you think about the fluctuation due to waves or tidal effects and so on that are much higher. So even here, you have to put a lot of science in order to extract this information. Of course, I know, let's say, for a number of these things, which is the process. So I believe with no problem about this process, but normal people maybe not. But if you go to the melting of glaciers, you can go and visit or look at pictures. And here you don't have to think about precise measurements, but these are macroscopic measurements. We are speaking about meters, hundreds of meters, kilometers sometimes in some cases. And I showed just a few pictures. These are pictures of Mont Blanc. And here you see after, let's say, more than 1 century on the left panel, a lot of ice was lost. But just in the last 30 years, in the bottom right panel, you see a great differences. A lot of ice lost again. You could say this is one point, one place, and local phenomena does not, let's say, mean that globally is the same. But if you go to, I don't know, USA here, you can see the, let's say, retreat of the glacier in this USA glacier, which is absolutely macroscopic. And you can go to another glacier in the USA and in Alaska, and where things comes from, let's say, here from hundreds of meters. We are speaking not of hundreds of meters, but of kilometers. This one is incredible now, almost more than 6 kilometers lost. So, here we are in Nepal, similar things, and again in Peru, and just spanning different places. In Antarctic melting, this is just one day for the record. You see how dramatic this kind of things can happen, even in few days. So, let's say, this is not something you have to believe thanks to scientists. This is something you can believe just looking at the photos or visiting directly these glaciers, because there are, of course, traces of their previous levels visible also going there. Globally, in every place of the world, glaciers has reduced a lot, except here. You see one point over the India, close to the western part of Nepal. And it's not surprising, because when you change the dynamics you can have a local, let's say, cooling, even if globally you have a strong warming. Because, I mean, you change the dynamics of the atmosphere, so maybe, let's say, a cold flux of air masses in a place can increase, while in all the other places, warming is, let's say, affecting glaciers or other phenomena. So, let's say, this is important to say why glaciers are also relevant. Because, I mean, when you have melting, you are absorbing latent heat. So if you have melting, it means that you have more heat than before. And note that this means that you all know that we are in the process of, let's say, going from solid to liquids, or melting or freezing, depending on the direction. Of course, you don't increase your temperature. Temperature is constant. You are just absorbing or releasing latent heat. The same happens for vaporization or condensation. So when, let's say, glaciers are melting, it means that they receive much more heat than before, so much more energy. And at the same time, they are, in a certain way, damping the effect on temperature. Because, let's say, thanks to their melting, temperature locally, I mean, where they are, is not changing so much. So, let's say, consider that glaciers are even mitigating the increase of temperature that we are measuring. But as they are reducing, these mitigation effects will decrease. But as they are integrators in the years and the tens of years, even centuries of this heat, let's say, if they are melting all over the world, it means that we have much more energy in our planet, at the surface of our planet. So from now, please, if you meet people who say that global warming is questionable, you have to know that either they are ignorant completely of the matter, or they are liar and they know that they are lying. So this is something that have to pass clearly to your students. Don't look at complex measurements of temperature of sea level rise. Look at glaciers, and you cannot doubt about the global warming. But there is another question. Why the climate is changing? Because it could be the external effects, no? And so maybe it's not the problem, let's say, it's not something related to our, or mainly related to our human activity. If you look at climate evolution in the past, there are fluctuations. Look at the scales here, they are changing very dramatically among different panels. So, I mean, each panel on the left is sort of zoom of the last part of the panel on the right. Okay, at the beginning of the planet existence, we have just estimation made by geology, but we want to concentrate on this last, let's say, I want to say 800,000 of years before our present. Something that, if I am correctly understood, Joachim has mentioned this morning, and probably you have discussed about it yesterday. We know this temperature with, let's say, a comfortable precision because of the ice cores that has, let's say, an information about it. So, I mean, you see here in the last 800,000 century before, that we have in our planet several fluctuations. And probably you know that if you look at the CO2 concentration here, there is an apparent correlation between these two phenomena. Is it something that enables us to say, okay, more CO2 means is higher temperature? I want to say clearly, not. So don't say, students, that from this it's clear that if I had more CO2, I have surely more higher temperature because of this graph, of this picture. Why? First of all, errors. CO2 concentration here are, let's say, directly measurement from microscopic gas bubbles. So, I mean, you take the ice and you have to extract this. And of course, this has some errors. that here are not reported but exist. Another point is that the temperature here are not measured through a thermometer put on the ice, of course. These are temperature measured through an indirect way using isotopes of hydrogen and oxygen. The basic process is that different molecular weight due to the different isotopes, let's say, react differently on, let's say, availability of heat for, let's say, to transform from, I mean, for evaporation. So, I mean, higher, let's say, higher weight molecules, let's say, respond in a different way to, let's say, changes in temperature. So, I mean, the final percentage of these isotopes change according to this different evaporation linked to different temperatures. And this evaporation affects the precipitation of snowfall at poles that, let's say, accumulate these. And so from this point of view, measuring ice core is not a local measurement. It's much more global than you could imagine. And of course, than measuring directly temperature at the. So from this point of view, this is a good news. But the point is that the process that, let's say, brings these dynamics is very complex. In the sense that here I have a clear correlation between these two parameters, but I have no information on the cause-effect relationship. This is typical of statistics. I know that something is related to the other one, can be directly, can be thanks to another parameter that drive both of them, but I don't know which is the cause and which is the effect. Physics say that if you add CO2, you increase greenhouse effect, and we see in a minute. But it's also true that if you change temperature, you affect the biosphere, and so you could have an increase of CO2 because of effect on the biosphere. And so you don't know exactly which is the cause and which is the effect. Then another important point is that here CO2 has no anthropogenic origin. So you cannot say, okay, if you add CO2, clearly you increase temperature, because who added this CO2 at that time? I hope it is clear that these graphs can be very misleading. And in fact, the mechanism is very complex, and the Nobel Prize Parisi, let's say, won the Nobel Prize in 2021, let's say, gave an explanation of this. What we know is that temperature changes triggered probably by fluctuation in the Earth orbit, so for astrophysical reasons. But we know that it's not enough. I mean, this changing in orbits parameters does not account for the energy that is necessary to make this changing in temperature. What we know is that, let's say, atmosphere is a chaotic environment, a chaotic system. So from this point of view, what can happen is that if you have a chaotic system like this one here, you can go from one point to the other, even with, let's say, not enough energy to do this jump, because noise, in this case, as fluctuations due to, if you want, the meteorology, can help you to have some chances to reduce this gap and allow you to go from one state to the other. So you need some external trigger that force you to, let's say, make to go a little bit uphill, but you need also some feedback and some noise to do this. This is called stochastic resonance. So probably the explanation of this one is that we have a trigger, let's say, astrophysical trigger, and then an enhancement effect due to the internal fluctuation of the chaotic systems. Then probably this can generate also positive feedback. So of course, if there are something changing temperature that have an effect on CO2, then an increase on CO2, let's say, help to trap more energy on the surface, and so help to make this transition. Here you are looking at transition like the one that probably you've seen in the Lorentz model, also shown by Valentina this morning. But these transitions are complex to be explained. Not say that I had CO2 and I have this increase in temperature to students, because I mean, This is something not true. And the question is, but here there was no human effect. So if it's happening in the past, this means that if it's happening also now, we are not responsible for this. On the contrary, what is very, very relevant is that we know that CO2 is greenhouse gases, and that if we have this fluctuation in the past, now we are at this level, the one, let's say, circled by this yellow circle. So it means that humankind, because I mean humankind appeared more or less 1 million years ago, never lived in an environment, in an atmosphere with this level of CO2 concentrations. So this is one clear message. I don't want to say that this jump in a while with respect to geological, let's say, times that you can see here means that you have a jump in temperature. But we know that humankind never experienced this atmosphere. CO2 is luckily is not a poisoning gas in this concentration or even more, but it's a gas that physics explain that has a greenhouse effect. I'm running out of time, so very, very, very quickly. Composition of atmosphere is essentially constant, and the greenhouse gases are, let's say, methane, which is very, very low in concentration, CO2 more than methane. So methane is more efficient, but lower than CO2. Then we have water vapor, which is very variable, which is less efficient than CO2, but higher in its presence in the atmosphere. Measurements of CO2 are started from, let's say, 1958, and are constantly increasing. So greenhouse, and the same is happening for methane. And so, I mean, how does it mean? Why we are worried about, let's say, greenhouse effect? Because essentially what we have is this. You know that, let's say, the emission of radiation depends from the Planck law. Essentially, we have a relation between, with the fourth power, with temperature and the energy. Here we have the comparison between what, let's say, is the energy emitted by sun, which has, let's say, some thousand, let's say, roughly 5,000 degrees of temperature, and the Earth, which is roughly as, let's say, on average 15 degrees. So here energy is much less. Consider that this is the reduce of a factor of 1 million. So I mean the peak should come outside of not of the roof of the atmosphere, or if correctly projected. So he's reduced here, but because of course much more is higher is the temperature, higher is the energy produced. But when this energy arrives to the Earth, thanks to the distance of the sun, I mean the energy arriving at the Earth's surface and the one re-emitted by the temperature of the Earth should be the same, because we are essentially in equilibrium. We are not experiencing an increase of temperature every day, no, constantly. So I mean, there is a balance, and this balance is in fact represented by these two curves. Here is picked in the visible because of the frequency of the emission of the sun, and these are picked on the infrared. They are not overlapping, so it means that can be easily separated, even let's say if you have to measure, because you look in this frequency to measure solar radiation, and in these others to measure, let's say, Earth emitted radiation. Okay, so let's say solar radiation arrive at the surface, let's say, almost undisturbed. I say almost because 30% is reflected, so let's say sent outside without any specific interaction, most because of clouds, aerosols, and other parts because directly reflection from the surface of the Earth. But this radiation goes outside without particular problem, because at that frequencies, atmosphere is almost transparent. I say almost, not exactly, because some part is absorbed, but you know, the most of this is let's say, goes outside without problem. On the contrary, the infrared radiation, let's say, the atmosphere is opaque to the infrared radiation, so to the emission of the Earth. Okay, so when we think about it, we think about this lower part of the atmosphere. Probably you know that the atmosphere has an average behavior with decreasing temperature, then increasing again thanks to ozone absorption of the, let's say, ultraviolet tail of the spectral radiation, then decrease again, and then increase again because of the ionosphere, so the absorption of the extreme ultraviolet thanks to nitrogen, oxygen, and some ions of them. But what is important? So, I mean, we have an absorption here of the visible and other part of the spectrum, an absorption here of the UV, and here of the higher energy part. But what is relevant is this part, especially for meteorology and for climate. In 2021, also another Nobel Prize, Sakuro Manabe, explained this process through a model. So its model was at the beginning, when it was, let's say, young, so it was in here 1960, let's say beginning of 1960 years, was very simple, and but the reason why he won the Nobel, because it explained this part. Okay, I have a balance at the top of the atmosphere. Radiation incoming, it's equal to the radiation going outside. But I have temperature higher than this equilibrium with respect to the formula related to the Planck formula. I have no time to explain this one. This part is due to the natural greenhouse effect. But if we increase the greenhouse effect, what happens is that, I mean, the transparency of the atmosphere reduces. So what I can expect is a warming of the surface temperature, but pay attention, a cooling of the top of the atmosphere. Because here I have a sort of more efficient coat. So if I had a global warming, but also a warming on the top of the atmosphere, this can be due to external factor. I have more energy coming from, for example, astrophysical origin. But if I had an increase of temperature on the surface and a decrease of temperature in the higher part of the atmosphere, this is due to the increasing efficiency of the, let's say, covering effect of the atmosphere, so the greenhouse effect. He makes this model, founding this increase here and decrease on the strong decrease on the top of the atmosphere of the temperature. And I mean, the genius was that he put inside in a very, let's say, clever way also the feedback of the water vapor. Because I mean, he discovered that more energy means more water vapor in the atmosphere, means a positive feedback. So the final result was that if you double the carbon dioxide, you have an increase of 2.3 degrees. At that time, the reference level was 300 parts per million. Now it's 400. If you, let's say, if you double, you have an increase. If you, let's say, make it half, you have a decrease of the same. Without the feedback, it's much less. It's much less. So positive feedback are absolutely crucial in climate projection. And this is what happened several decades after his studies, that we measure this increase of surface temperature, but pay attention, we measure a decrease in the, let's say, lower stratosphere, so about 20 kilometers of height. This is the clear signature that this is not an external phenomenon. This is a phenomenon related to greenhouse. So as the greenhouse gases are increasing thanks to, let's say, now, thanks to the action of humankind, we are responsible for global warming. This is things that have to be explained to students. We have this signature. These are measurement from satellites. These are from radiosonde. We have some peaks due to effect of volcanic eruption, so dust in the stratosphere, so more capability of the stratosphere to interact with the radiation. But when this effect, let's say, goes down, you see that the trend, apart from the last year, is, let's say, a decrease of temperature. This is the signature of our responsibility. Well, more complex models has been developed by the same scientists and also other groups. And the final discovery was that if I increase greenhouse gas, I increase the downward flux, I increase the surface temperature, I decrease the stratospheric temperature, I increase evaporation and increase in precipitation. but in a different way, because I increase precipitation where water is already in the water-rich regions, while I decrease locally, let's say, because of changing in circulation. These are model results, so they are be taken with, let's say, consider the errors. They are decreasing where you have semi-arid regions. So let's say we should experience, and we are measuring it now, an increasing contrast between water-rich and water-poor regions. We have to study more the atmosphere, more data, and I'm part of a satellite mission to be launched in 2027, which is going to measure for the first time in a, let's say, a spectral resolved way and systematically this part of the infrared spectrum, the far-infrared spectrum, which is responsible for a large part of the energy balance that at the moment is more modeled than measured, because this is important to catch, let's say, climatic feedback and to refine these projection models, the one that also, let's say, Noah was mentioning in this topic. Okay, just 1 minute. Are we hopeless, or we can do something? I suggest you this exercise I've done thanks to, let's say, I've done it by the former president of ASI, and I've done it again to check if really these are the figures. If you look at the current world energy demand now is this value, so 5.8 per 10 to 20 joule, and which is about 1 part per 10,000 of the solar incident energy. A little bit more if you consider that the part of this is lost by reflection. If you look, I've done an exercise for Italy. If you look at the demand of Italy, these are the numbers. 6 point, a little bit more, 6 than per 10 to 18 joule. And if you consider this demand of energy and you consider the solar average annual irradiation in Italy and the efficiency of panel, it results that if you want just producing this energy, this is global. I mean, transportation, industries, let's say civil use, whatever. So if you want to produce this energy just using solar panels, you will need 1,000 square kilometers of surface. Is it too large? Note that in Italy, we have the same areas just covered by parking areas. So something that you don't need, I mean, there's no particular reason why not to cover with solar panels. But if you look at these used industrial areas, so areas where are left there without any use at the moment, these are 9 times more. So when we say, is it possible to, let's say, go from, let's say, green renewable production of energy without affecting agriculture, let's say, cultural heritage, cities, and so on? The answer is yes, because we have a number of surface already ready to host these solar panels. And then just think about solar panels, not about wind and so on. And if you look at the cost of this price as, let's say, reduced dramatically the photovoltaic solar production from in the last 10 years with respect to other sources, for example, offshore wind already decreased a lot, but the coal not, the nuclear has increased because of the problem of waste, managing of the resulting wastes. So, you know, this is not something unfeasible. This is something feasible. And if we have a future with this renewable energy, eventually more than what we need for, let's say, present needs, we could think about a future where we can produce hydrogen thanks to hydrolysis. We can produce fresh water through desalinization, and we even produce plants for capture carbon and so extract carbon from the atmosphere and try to reverse the process. This is not a dream. I mean, these plants are experimental and seems they are capable to do it. They need a lot of energy, but if we'll be able to produce this energy in a renewable way, of course, these that can seem dreams can become, let's say, a reality. So now the core message is global warming is a fact. It depends on the greenhouse gases, and we are responsible for this, we can stop the process moving to renewable energy, not impacting on our, let's say, world in a way that is incredible. And let's say, if we don't do this, we expect, let's say, more energy, more extreme events, and so dramatic effects. The main question is the following, and I don't want to read it. You will read on your own, and sorry, I was too long. So again, but I hope that this, as a result, in some way useful for your, let's say, understanding and your work.
Thank you for this talk. Definitely something that we needed in order to understand that science is difficult. Science is serious, and we have to trust it. We don't understand all these processes, all these equations, and all these things. We cannot bring them to school in this level, but we have to trust it. This is the message. This is difficult stuff. This is serious stuff. And Noah said, in democratic societies, most of them, science is protected. There are institutions. There is investment in science. And we understand also through your talk how relevant this investment in serious science about the weather, for instance, is. We are very grateful for this talk. Thank you that you took your time to prepare this for us. And unfortunately, we won't have time for questions because we are a little short of time now. So we thank you again. And we continue our conversations. I will come to Florence soon, and I will have some questions to ask when I visit you. Thank you. Now So now I say goodbye, because we are a little short of time, and the next talk is already beginning with a delay. Sì, se poi if you want to stay to see the new talk, the next talk, which is completely different, it's about recycling and children. You can stay with us, and we will be very grateful.
And happy birthday
to your grandma, to your mother, or is it? Yeah, to your mother. Happy birthday to your mother. We are all wishing your mother.
I'm not able to hear you very well because.
Oh, I'm sorry, it's my fault. I wanted to say that I'm very grateful that you took your time to prepare this for us. We understood perhaps less than we thought that we were, at least I understood less than I thought I would understand, but I understood the seriousness of science very, very well. And I am grateful, that it connects to Noah's idea that democracies, well-functioning democracies, invest in serious science, and that this serious science is definitely necessary at the moment. And I am very, very happy that you have convinced me, and probably the others as well, how necessary it is. So thank you for your time. Oh, we do have a question. Then.
A quick thing that Laura Martino mentioned is that some of the examples that you made. I cannot hear.
Non può sentire.
Hello, can you hear me now?
Yes.
Yeah, okay.
No, yes.
Okay, so there are some comments that essentially the last examples that you mentioned about the solutions and how feasible they actually are, well, seem to be anyway, are actually quite striking. And like, it's really important to be able to have those examples, because they probably are the things that talk most to people that do not have a scientific knowledge, essentially. For example, you need 1,000 square kilometers of solar panels, and yes, that's initially when you say that, that sounds really big. But when you put it in comparison with the other things you said, not so much anymore.
Surprised.
Yeah.
I was surprised, in fact.
Yeah.
If you have any other
If you have any other examples like that, that would be actually super useful. But yeah.
for us.
Yeah, I mean, my suggestion is that you can do it for Germany, for example. I mean, I was hearing with a lot of interest also to the action that Noah was mentioning in the talk before. Let's say it's important also to put these figures and ask to politics, okay, we don't want only that you improve transportation and so on. We want this new production of energy. So in the political agenda, we need it. And I've spoken about solar, but that there is wind, there is tidal, let's say that there is energy that can be taken from tidal effects. And now, close to to the Alps, they are discovering, let's say, hydrogen reservoirs. So you can mine the hydrogen, which is a renewable source of energy. It's not like petrol because it's generated by geological ongoing phenomena like other happening, let's say, in the deep part of our Earth. So this is another thing. So we can go and use this together, but without thinking that it's very difficult, we need a lot of space, a lot of technology. This is false. And this is an important thing. I mean, probably, I mean, people do not know, even politicians, but who has the interest in hydrocarbon, let's say, market, of course, probably they know. But you know that the biggest, let's say, photovoltaic plants is going to be, or is already built in Saudi Arabia. So, I mean, they have a lot of petrol, but they have a lot of oil, sorry, but they have also a lot of sun. And they are aware that it's convenient now, more convenient produce energy through the sun than through extraction of hydrocarbons. So these are things that when you put them all together, let's say my suggestion for young people is not only go and protest, which is important, but go and ask and say, we know these numbers, we have make these studies, simple studies, and we want you to explain how you intend to use this surface to produce renewable energy in your political agenda. This is my suggestion, you know. But let's say, I was really surprised when I put together this, when I read these numbers, and I say, it's not possible. I want to make this computation again, and this was the result. So I say, okay, that's true. Do it for Germany too, and for the other countries.
Yeah, the computation of how much space was needed for covering with windmills. Thank you. Thank you again. Thank you.